Would be useful for running.
They're super useful, and that's actually where you get them. You get the running store in Henderson. You get them at the running store. Okay. Yes, the one next to the bouncy world or something. All right. So tomorrow we're gonna burn Cheetos and Doritos and Sun Chips and pretzels and anything else you bring in. If you have like cheese nips or Cheez-Its, you bring those in. So we're going to burn them tomorrow because we want to find out their heat content per gram. The unit we're working on right now is thermochemistry. Thermochemistry is the study of energy change. Changes due to energy or changes releasing energy. So sometimes energy is the cause of change, and sometimes energy is the result of change. After we do thermochem, we're going to do the second part of energy changes, and that's called kinetics, which is how fast reactions occur. Yeah, there we go. Now we're going to be talking about heat, energy, and temperature. And we need to remind ourselves about heat and temperature. I have a question for you. Does temperature measure heat? No. Good. No, it doesn't. Excellent. No. They're two very different things. If you remember, temperature measures what? Very proud of you. Yeah, temperature measures the kinetic energy of the particles. And if you remember from our kinetic energy unit when we did gases, kinetic energy is 1/2 mv squared. 1/2 times the mass of something times its speed twice, v squared. V stands for velocity, a fancy way of saying speed. We're going to learn more about velocity next year in physics. But remember, temperature measures the oomph of the particles, their mass times the square of their speed. Heat doesn't measure that. When we say something like, this ball has heat, we shouldn't say something like, this ball has heat. Now, if I blew this ball up, there would be a heat change. It'd be like inflated it, because particles would be going into the ball. So anytime there's a change, energy goes into or out of a system. But temperature doesn't measure heat. We measure temperature to measure the mass and velocity of particles. Now, when we add heat to something, that's going to cause the particles to speed up, which will produce a measurable change in temperature. Or if we remove heat from something, that's going to cause the particles to slow down, which will produce a measurable change in temperature. But they're not the same thing. Any questions before we move on? Okay. We're going to do our study about thermochemistry in 3 parts. First, we're going to talk about specific heat, how we study heat changes. Then we're going to talk about something called enthalpy. Enthalpy is specifically the types of energy changes there are in chemistry. Then we're going to talk about something called entropy and free energy. Entropy is chaos. Pretty neat. Okay. So we talked about this. Difference between heat and temperature. Heat is a measure of energy change in a system. I'll talk about that in about 20 seconds, what I mean by a system. The unit for heat is the joule, which is kind of neat. Joule is a crazy unit. It's used everywhere. In chemistry, we care about the joules that come from a thermochemical reaction, or maybe a nuclear reaction. In physics, we have electrical energy that's measured in joules, and we have work, or we have changes in motion that's measured in joules. So heat, all energy is measured in joules. It's named after a guy called James Prescott Joule, which linked the chemistry and the physics of energy together. And he did some pretty slick stuff that we'll talk about in physics if we take it next year. Temperature, once again, is a measure of average kinetic energy, and we measure our temperatures in Kelvin. So don't forget that we're measuring our temperatures in Kelvin. How do we turn a Celsius into a Kelvin? At 273. Now that's important because when we're looking at thermochemical reactions and we're looking at the temperature or the heat that comes in or out of them, we're going to be looking at changes in temperature. Now we remind ourselves that if we want to take a Celsius and turn it into a Kelvin, we add 273. But when you're looking at changes in temperature, it doesn't matter. Let me show you what I mean. If I take 20 degrees Celsius and I heat it to 30 degrees Celsius, what is my change in temperature? 10 degrees. Positive 10. Write that again. Okay, my change in temperature is positive 10 degrees Celsius. Now, if I take a temperature at 293 Kelvin and I raise it to 303 Kelvin, which is what these are, what's the change in temperature? Plus 10 Kelvin, yeah. So a change in temperature doesn't matter because we're just adding 273. So a change in Celsius and a change in Kelvin are the same. When you're doing any kind of absolute temperatures, we always use Kelvin. Does that make sense? Okay, now we classify a reaction as either exothermic, when a system loses energy to the surroundings, or endothermic, when a system gains energy from the surroundings. So, exothermic, think exit energy. Endothermic, think into energy. You learned in biology some things have exoskeletons, skeletons on the outside, and some things have endoskeletons, skeletons on the inside. Same words. But here's the crazy thing. When we're looking at experiments, not just in chemistry, but in all branches of science, what we do is we focus on one thing. And that one thing is called the system. So we look at something, we focus on the system. Like, if we wanted to take a survey of what everybody's favorite food was in this room, people in this room would be the system. We're not surveying people outside, we're going to call them the surroundings. We don't care about them. So what we're looking at when we look at thermochemical reactions is the system. Everything outside the system is called the surroundings. The rest of the universe is called the surroundings. So the trickiest thing about chemistry and thermochemistry is looking at what is the system, putting yourself in the frame of mind of if I am the system. Okay, an exothermic process. If you have an exothermic process in your hand, you are the what? You're the surroundings. So if the system is giving off heat, what's that going to feel like to you? The surroundings. It's going to feel what? Hot. Yeah. If you're the surroundings and there's a system that's undergoing an exothermic process, it's going to feel like to you to be hot because the system is losing heat going into you. However, if you would put yourself in the presence of the system would feel what? As it loses heat? Cold. Okay? So the system losing heat would be cold. But you're the surroundings, as the system loses heat, you're going to feel warm. Does that crazy idea make sense? When an ice cube melts, heat has to go what? When an ice cube melts, heat has to go into the ice cube. So if the ice cube, think about this, if the ice cube is a system, is the ice cube getting warmer or colder? The ice cube is getting warmer because heat is going into the ice cube to cause it to melt. Make sense? That's why an ice cube, when you hold it in your hand, feels cold because you're the surroundings. The ice cube is taking heat from the surroundings. You. So in an endothermic process, if you are holding an endothermic process, it's going to feel to you to be cold because you're not the system, you're the surroundings. We're going to do a couple of reactions in a couple weeks that actually do just that. We're going to do a chemical reaction and the beaker is going to get cold. You're like, oh my gosh, the beaker is so cold because the system is going in from your hand, heat's going from your hand into the system. What kind of reaction would that be? endothermic, right, endothermic. When heat goes into the system, it's endothermic. Okay, any questions? All right, so put your pencils down for a second. We're going to do a little experiment. With your left hand, put your left hand on your tabletop. With your right hand, put your right hand on the table frame, the wood part. Interesting. How do they feel? Cold and warm. Okay, that makes sense. I have a thermometer here, which has been in the room as long as these tables, and it tells us that the room is 23 degrees Celsius. If you're curious what that is in Fahrenheit, that's 73 Fahrenheit. So the room is at 23 degrees Celsius, which means the tabletop is at what temperature? Tabletop's at 23 degrees Celsius. And the table frame is at what temperature? Yeah, the same 23 degrees Celsius. Your hand, something you should know, your hand has only 3 fingers. Your hand is at 37 degrees Celsius. So your hand is at 37 degrees Celsius. That's body temperature. So when you put your 37 degree hand on a 23 degree tabletop, heat goes where? Into the tabletop. And when you put your 37 degree hand on the table frame, heat goes where? Into the frame. But how come one of them feels cold and one of them feels warm? Why is that? Don't overthink it.
Why is that?
Why is that? Why does this feel cold and this feels warm? We'll get to that. It has something to do with specific heat. But don't overthink it. In your own words, why is it different?
Different materials.
Different materials, exactly. They're different materials. The materials that make up the tabletop are very dense. The particles are very close together. The materials that make up the table frame, far less dense. So that idea that the materials of something causes heat transfer to be faster or slower is specific heat. If you like book definitions, here's a definition for specific heat. The heat energy required to raise 1 gram of a pure substance 1 degree. I like to think of it as how a substance reacts to heat, or its resistance to heat. And if you like physics terms, I like to think of it as the thermal inertia. So specific heat is how a substance reacts to heat change. Or another way to think of it is its resistance to heat change, or resistance to heat movement. Does anyone remember what inertia is? You learned this years ago. When?
Forces acting on something that's moving.
Okay. Yeah, we're getting there. Inertia is a big deal in physics. Inertia, I like to say inertia is a teenager in bed will remain in bed until acted on by a parent. Or a teenager at a party will remain at the party until acted on by the police. Inertia is an object in rest will remain at rest. The object in rest will remain at rest until acted on by an outside force. An object in motion will remain in motion until acted on by an outside force. It's mechanical inertia is an object's resistance to movement. Thermal inertia is an object's resistance to heat change, or heat. So, which thing has more resistance to heat flow? The frame or the tabletop? The frame. The frame has more resistance, which is why when I take my 37 degree hand and put it on a 23-degree tabletop, it feels cold. But when I put my 37-degree hand on a 23-degree table frame, it doesn't feel cold. The heat is moving out in both cases, but in this case, it's moving a lot faster. In this case, moving a lot slower. Yeah.
How extreme can that get?
Extremely extreme.
So like, if it's just 23, could you actually be like, your hand like freezing on this, but not on this, just because you think it is? Feels like it? Even though they're the same temperature.
No, because eventually you're going to warm up the general region around your hand to the point where the heat flow is going to get slower and slower and slower and slower. There's this principle called Newton's law of cooling, which states the bigger the difference in heat, or the bigger difference in temperature, the faster the heat will move. So eventually it will slow down as you heat it up. But yeah. There's these really cool plates, and they were called quick thaw plates, and they were basically a chunk of copper or aluminum that you put your steak on, and then they just thawed the steak out in like 20 minutes instead of 2 hours. Pretty cool. Every time I go to Savers, I look for them. So it's a property of matter. Different materials have different specific heats. Now, if you're going to make mac and cheese, you're going to cook dinner for your parents because it's Wednesday, so it's your turn. You're going to cook dinner for your parents, and you're going to make mac and cheese because you're a kid. Like, mac and cheese. Are you going to stir your boiling pot of mac and cheese, the water, just the pasta, are you going to stir that with a metal spoon or a wooden spoon? Why not a metal spoon?
Because the heat will conduct.
Yeah, because the heat's going to conduct through the spoon a lot faster. Will the 100-degree water, will it transfer heat into both spoons? Yeah, but it's going to transfer heat into the metal spoon faster, exactly. So, we use the symbol C for specific heat, and the little p, subscript p, means at constant pressure, meaning at our environment. Sometimes you see CS, and for some reason, every now and then you see specific heat given to you as S. I'm going to always use, or try to always use, the variables the College Board uses, because many of you will go on to college. Some of you will take chemistry AP or physics AP. So I try to always use variables that the College Board uses so you can recognize them. But just realize that sometimes you will see specific heat given an S, including one of the videos I'm going to show you later on. But yeah, use C. Okay, more about specific heat. Metals have a very low specific heat. The molecules are very close together. When we vibrate them, it causes a lot of the molecules to vibrate very, very rapidly. So when molecules are close together, they tend to have a pretty low specific heat, a pretty low resistance to heat change. In fact, while it isn't a rule, it's a pretty good trend that your more dense materials will have a lower specific heat. Copper and silver and mercury are very, very dense, as is gold and lead. These are very dense materials. They have very low specific heat. Wood, air, not very dense, much higher specific heat. And then there's water. That beautiful substance that you're made primarily of, water. When, on a cold day, you go outside to get the mail, do you immediately start shivering? No, because you're made out of water. You're warm-blooded. And then a really hot day, you go outside to get the mail, you immediately start sweating. No, because you're warm-blooded. Your body has a very, very high resistance to heat change. So, there you go. So water has a very high specific heat. And this is a number you're going to use a lot, 4.18. Okay. 4.18 is the specific heat of water, and you're going to use it a lot. It's something we call calorimetry, which is what I'm going to show you later on today. So, in summary, substances with a low specific heat will change their temperature more rapidly. It will require less heat to change their temperature. Substances with a high specific heat will require more heat to change their temperature the same amount. Joules per gram degree, yeah. The unit is joules per gram degree, and I'll show you why that is for our next formula. Yeah.
Why is zinc all the way up to the top?
wondered that same thing too. I don't know. You'd think it would be like down here, and they'd move everything and put brass down here next to copper. I don't know. Someone just,
They ordered it by,
yeah, I have no idea.
on the right side they ordered it that way.
I just pulled this, I pulled the table off of, I copied and pasted from a textbook page.
Yeah.
That's what we got.
Thanks.
Okay, so, yeah. So, high specific heat, lots of thermal inertia, takes a lot of energy to change the temperature. Low specific heat, low thermal inertia, doesn't take as much heat to change the temperature. So there's got to be a formula involved. And the formula is one of my favorites. As cool as PivNert was, this formula is even better. Okay. So specific heat of water is 4.184. In case you encounter a calorie is 4.184 joules. In case you encounter that, it's been pretty much, calories not a standard unit, it's an imperial unit. It's what you see on the side, the back of your Snickers bar, as long as you're in the US. If you go to Europe, your Snickers bar will be measured in joules, thank goodness. But as long as we're still using this imperial unit, calorie. Okay, so our formula. Changes in heat is given the letter Q. Why Q? Because H was already taken. So H was already taken, so change in heat is given the letter Q. And we want to talk about a thing, so we want to use our mass. When we're talking about changing the temperature of a thing, we're going to use mass. And then our specific heat is, of course, given C. And then what's left? Change in temperature. So the formula, one of my favorites, is Q equals MC delta T. MC delta T. I'm going to bring some heat to this party. I'm MC delta T. Q is MC delta T. So, in other words, the amount of heat that you're going to put into a system is going to change the mass of that system, multiplied by its specific heat, multiplied by the change in temperature. This party is lit. I'm going to add some heat. I'm MC delta T. So let's unpack this. If you want to change the temperature of something a lot, if you want a big delta T, it's going to take a big Q, a lot of energy. Similarly, if you want to heat up something that is large, it has a large mass, the larger the mass, the more heat is going to be required. And finally, the larger your specific heat, the more heat resistance you have, the more energy it's going to take to change the temperature. This is why we use water in your radiator. Water has such a high specific heat, it can take lots of heat from your engine without changing its temperature a lot. Makes an excellent coolant. Questions? All right, let's do some calorimetry. Calorimetry, which I'm going to show you in a little bit, is using this stuff, where we're going to use our formula to do a specific heat exercise. So read this in your head as I read it aloud. Determine the specific heat of 34 grams of an unknown material if 485 joules of heat are absorbed to change the temperature 20 degrees. So let's go ahead and unpack this. Determine the specific heat of 34 grams. What variable is this? M. 34 grams, it's our variable M. Of an unknown material, if 485 joules, what variable is that? Q. There's our heat energy. Heat are absorbed with change in temperature by 20 degrees. What variable is this? Delta T, yeah, change in temperature. So we have Q equals MC delta T. If you don't have your calculator, go get one, and let's do this together. Unless you can do it in your head. Do you need a calculator?
I couldn't reach. That was so strong.
seeing some calculators that are down. You're still banging on them. Give me a thumbs up. Without giving me the answer, give me a thumbs up if you have an answer. Okay, take another 10 seconds. All right. If you got a number smaller than 1, raise your hand. All right, what'd you get?
0.713.
0.71. 0.71, and the units I'm not going to worry about. Okay, so our specific heat is 0.71. Good?
Yeah.
What kind of material is this most likely? It's probably a metal. It's probably pretty dense. It's probably a metal. Because if you're looking at something less than 1, it's going to be most likely a metal. Larger than 1, most likely a non-metal.
Yeah.
Okay. Any questions about that before we move on? Okay, one more. Now we've got a little more complexity here. If 950 joules of heat are added to 5.4 milliliters of water at 280 Kelvin, what will be the resulting temperature of the water? Yes? That's a great idea. So one of the things we should remember is that the density of water is 1 gram per milliliter. So 5.4 milliliters has a mass of what? 5.4 grams. What's it asking for in this case?
The resulting temperature.
Resulting temperature. So we're going to add our change in temperature to our 280. We're going to use our 950 joules. Mass is going to be 5.4 grams. Specific heat of water is always what? 4.18. Good. And then we're going to solve for delta T. And your temperature final is going to be your change in temperature plus your temperature initial. So go ahead and bang on the calculator for a while and see what you get. Okay, who got a number for the change in temperature? Bigger than 10? Bigger than 20? Bigger than 30? Bigger than 40? Bigger than 50? What did you get?
For the change?
For the change.
I got 36, but I think I did it wrong.
What did you get? 42. 42?
Yeah.
Can I round that down to 42? So 42. So the temperature final would be 322 Kelvin? All right. All right. Yes.
So what? I thought you had to find the. Okay, so I got 42, but I thought you had to take away from there.
Nope. That's going to be, this is the mass of the sample. Okay, so what do we use all this for? Well, if you've ever been wondering why or how they get the numbers in the back of your Snickers bar, they blow it up. They blow it up. They do something called calorimetry. They put a sample in a container, add a whole bunch of oxygen, and then blow it up and figure out how much heat comes out. You're going to do the same thing. I'm going to demonstrate it. So calorimetry is used to determine heat content of things. And what they do is they put it in a container, and then they allow a reaction to occur. The heat is released from that reaction, and it goes into water. and we measure the temperature change of the water.
So if it has 0 calories, it doesn't go up.
Yeah. Nowadays, they'll use computer models instead, because computer models are actually pretty good. But back in the old days, they didn't have computer models. So I have some nitrocellulose right here in a flame. How can I tell how much heat is going to be released? Blow it up. Sorry. Yeah, blow it up. So that's what we do. We do this. We take a device like a can. I'm going to turn the light on so you can see this. We can take a device like a can, and under the can, or into the can, we put a sample. So I'm going to put a sample. Tomorrow, you're going to use Cheetos, Doritos, Sun Chips, and pretzels. Standing in for that will be some nitrocellulose. I'm going to put it down. And I'm going to put it into my calorimeter. Into my calorimeter, I need something to measure. So that's where I get some water. I'm going to put some water in a test tube, and the test tube is going to go into the calorimeter like so. Okay? Then, we're going to need to measure the temperature change of the water, because when this thing blows up, where's the heat going to go? Into the water. And that's what we're going to measure. So we're going to measure it with a thermometer. These snazzy digital thermometers, they plug into USB. Get yourself a laptop. Totally love these things. Boom. Okay? So what you're going to do then is you're going to have a mass of water, which you're going to measure. You're going to use a graduated cylinder. The specific heat of water, which you know to be 4.18, and the change in temperature of the water you're going to get from your program. It's going to be the final temperature minus the initial temperature. That's going to give you a Q of the water. And we're going to pretend that all the energy that Cheeto lost, the water will have gained. So we're going to assume that whatever temperature change we have in the water, that was the energy lost by the Cheeto. Make sense? Now, this is what's going to happen. You're going to put it under there. You're going to light on fire. And all the heat's going to go into the water. And you're going to watch the temperature on your computer go whoop. Super neat. Questions? That would be hugely wasteful. But it would go woof. And there'd be a big bright light and there'd be smoke, and then we'd be like, open the doors! We're going to set the fire alarm off. I don't know what it'll take to set the fire alarm off in here. I really want to. But last time I asked a principal to turn the fire alarm off or tell the fire department not to show up, he forgot to do that. So they showed up. But anyway, so that's what we're doing. Now the last thing we're going to talk about before we're done today is we want to know the heat content per gram of the food. So what we're going to do is we're going to take the Q of our sample and we're going to divide it by gram. Specifically, gram burnt. So what you're going to do is you're going to put your sample on your sample stand and you're going to weigh it. Then you're going to burn it and you're going to weigh the husk left afterwards. And it will be like this nasty husk. You'll be like, that's what my body does? Yep, that's what your body does. We're going to use snack foods. Okay. Questions? That's calorimetry. Are there any questions? All right, cool. So you can use the remainder of class to work on whatever you want to work on.